Okay, so people are starting to file in. So when you have a minute, just take a look at this poll question and let us know where you're located. I'm just going to wait a little bit while people join the session here. So it looks like a lot of people are from Ontario, but we have all the way from Alberta to the Atlantic provinces and someone from the States as well. So, oh, now we got from almost, oh yeah, we do have coast to coast, Jeff. We got coast to coast. That's great. Love to see that. All right, so let's just see how many people are in. Okay, so it looks like most people are in and have answered the poll question. Thank you. I'll show you that so everybody can see. So it looks like most people are from Ontario here, but from BC all the way to Atlantic provinces. Excellent. One more poll question for you. We want to know what occupation you're in. So let us know what of these occupations best suit your career role that you're in. And if you do not see yours listed, it's other, just let us know in the chat and we'll take a look at that. Okay, we'll just wait for a few more responses to come in. Okay, that looks like most of the people. Wow, looks like we've got representation from every group except renovators. There we go. So mainly builder developers, engineers, architects, utilities, government. So right across the board. Excellent. Okay, so I'm just going to stop sharing that. So welcome everyone. My name is Stephanie Coleman, and this is the Geothermal Technology session with Jeff Salazar, who is from Enbridge. So thank you so much for joining us. Just a little bit of Zoom housekeeping before we get started. You'll see in the portion along the bottom of your screen a Q&A function. So if you have any questions for Jeff, please use the Q&A function. And what we'll do is Susan, who I'll hand the mic over to in a moment, we'll be monitoring that and she will ask Jeff the questions as we go along. Please use the chat for any general comments you have, or if you have any sort of technical issues, just let us know. I'll be monitoring that behind the scenes, and also, or you could reach out to me by email as well. After the session is over, probably by about tomorrow when the recording link is available, I will be sending out a resource email that includes the slide deck that you see today, as well as the recording link so you can view this again. And there's just some additional information, including SurveyMonkey link and that sort of thing. So at the end of today's session, when we end it out, a little box will pop up and the SurveyMonkey link will be in there. And if you have a moment, just fill that in. If you don't, I'll also send it in the resource emails, just because we'd love to get your feedback. So now I'm going to hand it over to Susan Cudahy from Enbridge Gas. Susan.
Thanks, Steph. And thank you to everyone for participating today. So just on behalf of Enbridge Gas, I just want to welcome everybody to today's session. We've got some really exciting content on new programming that we're going to be presenting today. And so I'm really confident that you're going to enjoy our guest speaker. You know, as some of you may have heard me say in the past, and you may be aware that Enbridge is actively engaged in an energy transition strategy, and that's to extend and expand our offerings menu and to really positively address the need for greenhouse gas reductions. So although we realize that the use of affordable, safe natural gas is still in high demand, and it's going to continue to be for some time, we understand that there's mounting pressures on builders from a variety of areas to meet the requirements for climate change actions, right from the municipal level up, and that leading builders are undertaking some of these new and innovative ways to meet some of those needs. You know, as a company, we know that a successful future for energy will require working in partnership with electricity and wind and solar, and more importantly, today's topic, geothermal. It's this type of partnership that we need to maintain an energy system that's affordable and practical for Canadians. So Enbridge is working towards a future where we can be your energy partner of choice, regardless of which avenue you take. So for today, I'd really like to introduce our guest speaker. Jeff Salazar is Enbridge's geothermal specialist and part of a broader business development team, all of which are working on low carbon heating solutions for residential and commercial applications. He provides really strong technical and operational insight from his over 20 years experience in the HVAC sector. He is a certified geothermal designer and installer, and he holds multiple trade certifications in various disciplines. So we're really happy that he could be with us today. And with that, I'm going to turn it over to Jeff.
Thanks, Susan, for the introduction, and thank you, Stephanie and Building Knowledge, for hosting us today and allowing us to get this content out to the public and all of the attendees for attending today. I am going to just share my screen here and get started. Stephanie or Susan, if you can confirm the screen is up.
It's up, Jeff.
Great. Okay, well, let's get started. Today we are going to talk about geothermal heating and cooling systems as opposed to geothermal direct use or geothermal power systems. These type of systems are used for heating and cooling as well as domestic hot water production in buildings and both commercial and residential. So let's get started. One of the first questions that usually comes up when I present this material, and Susan touched on it a little bit, is Enbridge is a gas company. Why are we looking at geothermal? And Susan did mention we do deliver safe, reliable natural gas to over 3.8 million customers here in Ontario. But we are striving to be the energy provider of choice. Some of you may know that our parent company, Enbridge, is heavily invested in renewables, and we have been for over a decade, including offshore wind, solar assets, and we're now thinking geothermal fits into this bucket of renewable assets as well. It's part of our energy transition planning. And it's going to help us and municipalities and our customers, as well as builders and developers, meet the climate and emission targets that are being set at all levels of government, to be honest, from federal to all the way down to the municipal level. We feel here at Enbridge that large-scale, low-carbon options are going to be required for that effective energy transition. And we feel we're strategically well placed to execute on those strategies. We're a trusted partner to municipalities, developers, and builders, and we have over 100 years of energy infrastructure experience. So geothermal, as you can see on the image on the right, fits well into our current business model. It is a below ground energy asset that requires significant capital investment, specialized skills to install, and it works very similar to our natural gas system, where the below ground network would provide the source energy to the indoor heating equipment. So with that and the comments on climate and emission reduction targets and strategies and policies, I think we'll launch another poll question if we could, Stephanie. And that first poll question is, have you experienced from any of the municipalities that you work closely with an expectation to build to levels higher than code? And looks like Stephanie's got that poll up. We'll give you a few seconds to answer that one. Okay, looks like it's about a 50-50 mix almost, or some of the municipalities. And we've noticed that in Ontario, several municipalities are very aggressive with their climate energy plans and their targets. Some of the smaller municipalities are slower to produce those new policies, but they are coming. And hopefully this technology will help some of the people on the call today get to those targets and meet them for the municipality and or the federal and provincial requirements. So let's get into it. Geothermal, what is it? How does it work? It's often referred to by many names: geo-exchange, ground source heat pump systems, ground coupled heat pump systems. Regardless of what you've heard it referred to as, it is a clean renewable energy technology that's utilized for heating and cooling of buildings, as well as domestic hot water production in many applications. These type of systems produce over 300 to 500% efficiency, which is drastic compared to current fuel-based systems, which are less than 100%. They also create zero on-site carbon emissions associated with that heating and domestic hot water production. So they're great for the environment and for the climate target. They are in use in Canada and North America, worldwide, especially for over 30 years. So this is a proven technology. It's been around for a long time. It has had its hiccups and failed to really meet mass adoption, but we're working towards that, and hopefully we see this picking up in the very near future as a go-to solution for your space conditioning needs. How does it work? Well, it utilizes heat pump technology. Heat pumps are a very simple technology. They've been around for eons. Your refrigerator in your home is a heat pump, essentially. And they're basically a technology that moves energy from one location to another. When you couple these heat pumps with a below ground network of a heat exchanger or ground loop, it basically connects the heat pump with an unlimited supply, not unlimited, but a supply of energy from the earth. And that earth acts as a thermal battery, which allows both rejection of energy in the summer months and pulling of energy that's collected from solar radiation throughout the year. So these systems are suitable for various applications, from single family homes to commercial high-rise buildings, multi-unit residential buildings, and entire communities, as we'll discuss later on in the presentation. So there's two main parts to these systems. Geothermal is built from a heat pump, as we mentioned, coupled to a below ground infrastructure of piping, which is considered a heat exchanger or a ground loop. Heat pumps are very simple technology. They use a vapor compression cycle, and which leverages the phase change properties of various synthetic and natural refrigerants as of late, to facilitate an exchange of heat from one area to another. So in a ground source system, we're essentially transmitting energy from the earth to the building and reverse. So it's a fully reversible cycle, which provides both heating and cooling, and can also be used, as I mentioned, for domestic hot water. There are multiple configurations for heat pumps currently on the market. We could move energy from air to air, which would be an air source type of piece of equipment. You can move it from water to air, which is a geothermal system that with forced air distribution. And there are also water to water heat pumps, which can convert the energy from the ground loop into a water system or a hydronic based heating system for in-floor radiant heating, using fan coils potentially. But heat pumps have the benefit of longer lifespan, especially ground source equipment, because it's typically located inside the building. And they're very efficient because they are simply using a unit of electricity to harness and move additional units of energy from one location to another. That's where we get the 300 to 500% efficiency out of these systems. So on that note, the one thing that makes these smarter and more efficient is that coupling to the ground or the earth. Deep earth temperatures in Ontario here range between 10 and 15, but typically hover around 10 degrees C all year. Whereas on the opposite scale, above ground, temperatures can fluctuate from minus 30 on a Sudbury Saturday night in January to plus 40 in Southern Ontario with humidex in the dead of July or August. So having that coupling to the ground source really provides that steady year-round consistency of these systems. And if you look at the table on the right here, the red bar is an air source heat pump efficiency. And as you can see, when the temperature drops down into the minus 10, minus 15 range, that heat pump efficiency drops because it's much more challenging and much more difficult and requires a little more energy to harness that heat energy from the outside ambient air. With ground source systems being coupled to the ground, it makes it steady throughout the year. So it produces a nice steady sort of efficiency throughout the year without those fluctuations dependent on weather. So the second part of these systems is the ground heat exchanger. And this is really where the magic happens. We're using the battery, or the earth as a thermal battery. So it provides a heat source in the winter because it's not exposed to the colder elements above ground. And in the summer, it's a large heat sink where we can reject unwanted energy from within the buildings to cool them and reject it into the heat into the ground, disperse it in there, and potentially recapture that later in the season when we need heating again. They do use a sealed system with a heat transfer fluid in the piping, and that fluid is circulated through that heat exchanger at a temperature that's lower than the ground temperature in order to facilitate that energy exchange from the ground to the fluid. The reason we put an antifreeze or a heat transfer solution in there is because the heat pumps are so efficient that they have the ability to remove and extract the energy. If you can imagine the ground's at 10 degrees C and we circulate a slightly cooler fluid into that ground loop, when it comes back and that heat pump removes that heat energy, the fluid going back into the ground would be close to 0 Celsius, which is near the freezing point. So to protect the refrigerant cycle, the heat pump, and to prevent freezing of the actual loop fluid, we add a small percentage of heat transfer fluid, or ethanol. Propylene glycol is often used, but it's a very low concentration of antifreeze to protect that system. In the summer months, again, the warmer fluid is passed into the heat exchanger, rejected into the ground, and it comes back into the heat pump in a cooler mode, which goes through that vapor compression cycle and produces cool tempered air or tempered water. These heat exchangers are made of polyethylene piping. Typically, there are a number of different materials that have been used in the past, but polyethylene is the most common used product currently, and it has a lifespan of well in excess of 50 years. So I have systems that have been installed that I've been working on that are installed as of the early 80s. So they're pushing 40 years old, and there's no degradation of that piping asset. It's a very robust pipe. We use it in our natural gas systems as well. So it handles pressure, it handles fluctuation in temperatures, and it's a really good long life asset that we're expecting to get closer to 100 years out of. So in regards to the heat exchangers, there are a number of different ways to install these systems, depending on the available space you have and the configuration of the system and the heating loads. Vertical systems are probably the most common now with the tighter building lots that we're finding, 40, 35-foot lots. They're very difficult to put in other than being vertical. So a vertical well is typically drilled to depths of 50 meters, sometimes 150 meters. We have technology that's able to go down as deep as 600, 650 feet even. And essentially what it is a 5 to 6 inch well hole that's drilled into the earth. And when the hole is drilled, the drill string is removed and a series of piping is put in, what we call a U-bend, which is basically a single circuit. And then once the well is filled up with that pipe, we backfill using a bentonite or a concrete type slurry that backfills and seals up that hole, which has two main purposes. One, to seal it off from below ground contamination. So if there's any water systems in the ground, it'll seal off that borehole so no groundwater will get back in and contaminate any of the ground below. And it also provides firm contact between the piping, which is the heat exchanger, and the surrounding soil so that we get good heat transfer through that piping and back into the building to supply that heat pump system. Typically, we would drill a single bore per ton. Sometimes you can do 2 tons of capacity per borehole. And there is a separation between the bores depending on the conductivity of the soil and the quality of the soil. We will separate them typically 10 feet minimum, sometimes 20 to 25 feet apart. And again, that the heat exchanger is sized according to the load on the building, the heat pump capacity, and the conductivity and qualities of that soil. These applications are suitable for new construction, especially in new communities with smaller lot sizes, as I mentioned. They are the lowest space requirement for installation of a geothermal system. We can fit these on 30-foot lots. And again, you can drill to very deep depth. So if you have limited space, you just simply go a little bit deeper and put more pipe in the hole. They do require specialized equipment depending on the type of soils. There's a number of different drilling techniques that work well. And the average installed cost is significant. It's $3,000 to $4,000 per borehole. So this is one of the major hurdles that needs to be overcome for ground source heat pump systems or geothermal, is that upfront capital cost. And we'll speak a little bit later as to our solution on getting around that hurdle. The second type, and this is a very common application in rural properties where you have acreage or a large yard to put in, a horizontal system is very effective. They're typically trenches that are dug 30 to 40 inches wide to a depth of 5 to 6 feet. Typically, the trenches are quite long, 300 to 500 feet. Typical circuit would be 600 feet long, which would fit in a 300-foot trench. So as you can imagine, you need a lot of space for this, typically a half acre of available ground space for a typical residential home. Again, all the piping circuits are laid and then tied together into a header system to bring a single supply and return line into the building, very similar to the vertical configuration. These are very common in rural properties, like I mentioned, not suitable necessarily for new communities, but in an application where you're doing potentially a community center or a large residential building that has available green space, potentially a park. Schools use horizontal systems very often because of the soccer fields or the football fields. Great technology, but challenging to put in tight spaces. These systems are flexible. They can even be installed to provide energy for entire communities. There's a number of different ways to do that. Network geothermal systems have seen a lot of press lately and a lot of interest, especially down in the northern United States. There's a number of projects going in, as well as in Austin, Texas. Whisper Valley is one of the largest. They basically leverage an ambient loop type application. So there are individual heat pumps in each building that provide the final tempered energy required for the thermal conditioning of that building. And there's one single interconnected ambient loop that runs throughout the property or throughout the community if it's a community-based system. So that heat exchanger system is connected to each individual building. There are multiple heat exchanger options that can be incorporated here. You could have verticals, as are shown in the picture here, and have a number of them throughout the community. You could also tie in a horizontal system underneath a park space or a green space, and interconnect all of those heat exchangers into the central ambient loop that basically distributes that thermal energy through the community, and the heat pumps harness that energy as required. These are great for medium to high density communities, especially when there's a mixed use of buildings in the community. So if you have a large number of residential family homes and also some commercial and retail space, or potentially a community center that has a year-long heating load or cooling load for ice rink or a pool system, these are great for energy sharing. There is the potential for one building. For example, if this building was a multi-unit residential and was cooling dominated, it would reject some of its heat energy into that loop field, which could then immediately bypass potentially the heat exchanger section and just go right to the next building and provide that waste heat as part of the heating source for the heating load in that additional building. So these are great systems. They are somewhat complex, depending on how they're laid out and the load diversity in the community. They often require below ground pumping vaults and a complex system of piping, but in certain applications where the energy sharing is available and those loads are diverse, they're a great opportunity to do an entire community with ground source heating systems. There's also other ways to do ground source in a community type application. Central plant geothermal district systems are common. There's a number of them here in Canada. The Europeans have really taken this approach many times in some of their applications. And essentially this would be a central energy plant, which houses multiple large capacity heat pumps connected to a single individual ground loop. So as you can see in the photo here, that the heat exchanger is not connected to the actual district piping. In this case, the energy would be harnessed or rejected into and out of the ground and used to source or provide an energy source for the centralized heat pumps in the energy plant. Those heat pumps would then produce high temperature or medium temperature water for heating purposes or chilled water for cooling, which is then circulated through the district system into each individual building. The difference between these is you don't require a heat pump in each building now. We're delivering usable thermal energy either in tempered water or chilled water, and a simple heat exchanger in the building is all that's required, typically a water-to-water heat exchanger. So the district energy heating loop would pass through one side of the heat exchanger, and the building energy loop would be tied to the other side, and the heat would just simply be transferred into that building and distributed amongst the various floors of that building or throughout the building to the fan coil units or potentially additional heat pumps or floor radiant systems, depending on how it's set up. These are typically a 4-pipe energy distribution system. So you have a dedicated circuit of piping for heating loads and a dedicated circuit of piping for cooling loads, which provides year-round heating and cooling, and also a domestic hot water source for all of the internal building or the connected buildings. Very simplified mechanicals, as I mentioned, at the building level on these. You don't need individual heat pumps, and much more cost effective as far as the mechanicals for the actual builders and developers. So we have another poll question coming up. Maybe Susan, if I can reach out, do we have any questions coming up through the Q&A that I can address now on the current subject matter?
I have a couple of questions, so maybe I'll just refer to them if you don't mind at this point.
Sure.
We have one question with regards to issues around leaks. So does ground source heat pumps have the same potential issue as air source heat pumps in terms of climate impact of leaked refrigerant, or does the ground allow for a safer medium to be used?
So yeah, that's a great question, Susan. So ground source heat pumps are a little bit unique and different than an air source heat pump technology because the equipment is located inside the ground, inside the building. There is fewer potential for leaks. They're factory charged refrigerant systems that are packaged within the heat pump unit. There's no field connections on that refrigerant piping, and the equipment being indoors allows it to be a little bit more protected than an outdoor air source heat pump that would be exposed to, especially if you're near the coastal environments where you have salt and corrosion from the seawater, but also freeze thaw cycles of typical winters and summers here in Ontario and throughout Canada. They really wreak havoc on the outdoor equipment, and air source heat pumps typically leak at the outdoor section in most cases. And because these ground source heat pumps are inside, they're protected from those elements, and they're also factory built. So there's no field errors that could occur that would potentially cause a leak down the road, like a potentially bad weld or any rubber seals that are exposed to that freeze thaw. So certainly a little more robust and less likely to leak than a conventional refrigeration system.
Perfect. Thank you. Maybe we'll take one more question at this point. We're jumping over some questions that have been posted, but we will during the Q&A go back and refer to all of them. So these are just for review right now. So question, how climate resistant are geothermal systems? For example, 100-year weather events, extreme rain, cold, heat events. We're talking here about their resistance to climate.
Yeah. So again, because of the design and the inherent simplicity of these systems, and also the fact that the equipment is protected, the heat pump equipment is protected indoors, and the ground loop is protected well below the Earth's surface, extreme weather situations don't really impact them, in my opinion. I'm sure there's been studies done on these, but because they're protected below ground, the heat exchanger typically is very resilient. It's not too worried about flooding. I mean, flooding we can't control. If we did have a 50-year or 100-year storm where we had one actually a couple of years ago in Toronto, where the riverbanks had overflowed and sort of run through people's backyards. Yeah, potentially you could have some erosion of soils, which would expose that heat exchanger. But because it is typically minimum 5 to 6 foot depth below the surface of the Earth, they are very well protected and resilient against climate events.
Okay, that's great. We have quite a few questions about cost, associated costs, but I know we're going to get into some of that further in the presentation. So just keep posting your questions and we will get to them at the end of the Q&A. Thanks.
That's great. Thanks, Susan. And we will address some of those cost issues as we move on. So Stephanie has another poll question here. Are you planning on including alternate energy sources in your future developments? If so, what options would you be interested in? So we have geothermal there. We have solar, which is really taking some traction lately. electric and other. If you have some other suggestions, please throw them in the chat. Give you a few more seconds to fill that poll out. Okay, so we have 77% are interested in implementing geothermal in future developments. That's great news. So we have a program for you. I will get into it a little later. Solar's second in line there, which is great. We're seeing a lot of net zero builders here in Ontario incorporate solar into their aspects. Geothermal fits very well with solar because it's an electric-based system with the invent of inverter-driven compressors. These require very low input to operate. There's actually a product I'm not going to speak to about today, but there is a product that has a solar integration with a ground source heat pump system that will actually allow the solar to run the heat pump during peak energy periods or excess solar generation to basically produce thermal energy that can be used at a later date when hydro is more costly to the homeowner. So that's great to see geothermal and solar being incorporated. Let's move on. So here at Enbridge, we typically don't jump into things lightly. We do like to test technologies and confirm that it's a viable business opportunity and a viable technology. It's going to be reliable for us. So we did do a pilot with a residential home builder here in Ontario. I'm not going to speak too much about it today. We do have another webinar that's scheduled with Quality and Buildability next week. I'll provide that link. That webinar, we will be getting into the nitty gritty of the actual geothermal pilot that we did with San Diego. Diego Rizardo from San Diego Homes will be speaking in that webinar with me. So if you're interested, we can certainly pass on the information for that. But essentially, the goals of the geothermal pilot that we did were to validate the technology and the performance of the heat pumps to confirm that they were operating at the COPs the manufacturers suggested, compare the energy costs of these systems versus base case natural gas equipment, which is sort of business as usual in Ontario here, and also to understand the implications to the construction processes around drilling and the loop installation. There have been a number of builders that have attempted geo in the past with mixed reviews. Sometimes the drilling rig would show up at the 11th hour and there'd be a mess on the property and they'd have to, regrade and resod at the end of the day. Or the drilling rig had some difficulties below grade that they weren't aware of. So it sort of pushed the construction timeline. So we wanted to really grasp what was needed to effectively implement this in a new construction atmosphere. We've been doing new construction with our builders for decades, over 100 years. So we have our systems and processes in place. We come in and do our servicing of that community, but we wanted to see how we could really perform and fit into the builder schedule without interrupting them by putting these geothermal loop systems in. The results were exceptional. We found that the systems provided 98% or greater of the annual heating requirements, requiring electric backup only a small percentage of the year, and they were sized to approximately 80% of that peak heating load. So sizing of the heat pump is critical on these systems, and we've recognized that. We also, one of the bonuses of these systems, we put de-superheater functionality onto these. So they were able to actually produce 40% of the domestic hot water load for the season. And that is a byproduct of the refrigeration process. So it's, I wouldn't consider it 100% free, but during the operation of the heat pump in heating or cooling mode, it will reject some of that excess energy in the refrigeration process and store it into a preheat water heater tank that basically limits the amount of time that the delivery tank has to actually produce that energy. So 40% it was exceptional. There was a 25% reduction in energy related costs for heating and cooling when compared, and domestic hot water when compared to a natural gas home. So we put 4 of these heat pumps in, and we also put energy and performance monitoring on a base case natural gas home that used conventional 95% efficient furnace with a conventional air conditioning system. We did see a 25% reduction in those energy costs across the heating and cooling seasons. which is significant because natural gas is cost effective, and we know that. So these systems do compete against natural gas, which is great to see. We also recognize the drilling techniques, the timing of construction, and the process improvements that were required in order to implement this. There are 30-foot to 50-foot lots being offered in Ontario. It's sometimes as low as 28 feet. So we've recognized multiple boreholes are not going to work in many cases. We do have the technology available to do single bores up to 600 feet, as I mentioned. So there is the potential to actually drill these loops in place prior to construction of the home. So we could, if we could GPS locate or stake out where the building is going to be, we can actually drill within the perimeter of the foundation of that property and drop that loop right inside the mechanical room or the future mechanical room to provide easy access, frees up space in the backyard for pools and outbuildings, and really gets into that construction process at the early stages, so we're not interrupting the builder's timelines. So as I mentioned, we are doing another webinar specifically on this geothermal pilot. We get into some video, some photos. Diego will speak to his builder experience on putting these systems in. And there is some content there and a highlight on how to register for that exciting webinar we're doing next week on the 21st. So please join us if you can, or if you're interested. So basically, I've told you how these systems work, what their benefits are, what the advantages are to energy consumption, climate change, CO2 reduction, and the construction processes that we looked at. And through the pilot and our research over the last couple of years, we have developed a number of programs surrounding this technology here at Enbridge. We will be offering these programs through an unregulated affiliate company. This won't be provided through the utility currently because we're approved to do geothermal activities, but our ratepayers are not going to be funding this. Essentially, it will be operated outside of the natural gas utility. And we have a number of programs, so we'll get into them now. Program essentially is going to, regardless of the program you choose, whether it's residential, community-based, or commercial buildings or multi-unit residential buildings, Enbridge will provide a turnkey geothermal infrastructure for each home or building in the community. There is no upfront cost to the developer or the builder or the end user, homeowner, or occupant of that building. We will convert the upfront capital costs into a monthly energy fee or a lease type application, which we'll get into a little bit later. And we also will cover the ongoing operation, maintenance, and the performance monitoring of that loop asset. Enbridge covers all aspects, the design, construction. We will even provide sales support for the builder communities, sort of teach their model home representatives or their sales reps on the benefits of the geothermal systems and what the customer is going to get at the end of the day. We'll provide some of that sales support, and we may be in a position to help with some of the marketing of that community as you implement these geothermal solutions. There are multiple options, as we discussed. Single loop per building is one common application. It's the most cost-effective and simplified design. Single loop per home, no interconnections with other buildings within the community. It's very cost-effective. We can also do micro-district applications, which are great for servicing, a block of 10 townhomes or potentially a MERB community that might have one or two mid to high-rise buildings on the same property. They're great, but again, they do get complex when you start doing larger communities and an ambient loop application. And we can also do full community systems with those ambient loops or central plant district systems using geothermal technology. The heat pumps, depending on the type of program and the type of application, in our single family, single loop program, the builder would be responsible for the heat pump equipment and the interior HVAC. We can provide them with a list of certified geothermal contractors that we would require them to use a certified geo contractor. One of the learnings from the pilot was that typical new construction builder HVAC trades are not well versed in geo at the moment. Not that they couldn't go out and get trained and certified on it, but it's a high volume, low margin business that has not historically fit in the geo industry. So hiring a geo specific contractor that knows the technology and knows the equipment is recommended. But the remaining aspects of the HVAC work in that building can be completed by the builder's typical trades, including ductwork, electrical, and plumbing connections to the equipment. That can all be done by the builder's existing trades. In the commercial aspects, it's typically build to spec, and that the mechanical contractors are more versed in heat pump equipment. So we don't see an issue in the commercial aspects or multi-unit residential buildings. So essentially, we've created programs to alleviate that capital upfront cost that has really stifled the market to date. The loop asset is typically 50, if not a little bit more, % of the upfront cost associated with these systems. So Enbridge is now going to be absorbing that cost and turning it into some type of long-term monthly fee associated with that loop asset. So we have developed a number of programs, as I mentioned, anything from a lease agreement for our single family, single loop applications, which would work very similar to a rental water heater process. The customer would sign in when they sign the agreement to purchase and sale that home. They would sign an agreement saying they're agreeing to pay that monthly fee, and we would charge a monthly fee based on the system capacity. So a 2-ton system would have a different cost as compared to a 5-ton system, and it's based really on the capital outlay that we have to put into that system, and is spread out over a longer period of term. We're looking at potentially 20 to 40-year terms, which will basically amortize the cost over the life of the asset at least. And they are fixed term contracts, but they do have buyout options. So very similar to the rental water heater program. Again, the customer can buy out from day one, or if they sell the home, they have the option to transfer that contract term over to the new homeowner, or they can purchase it outright and sell it as part of the building when they sell the home. As we get into commercial, multi-unit residential, or community-based systems, we're looking more at an energy as a service model where we would charge a flat fee monthly or a metered energy charge based on the system size or the gigajoules or kilowatt hours that we're converting into that building. Depends on the building type and the counterparty that we're working with. If it's a municipality for a municipal building, or if it's a builder or a community that's looking at incorporating this in multiple applications, we can certainly provide flexible terms. And with all our programs, we're going to provide a performance guarantee, and the commissioning, maintenance, repairs, and replacement of that loop asset is covered under the term of the contract for no additional cost throughout the term. That's part of the technology risk. We are absorbing that as well as the service provider. Whereas if a homeowner just went out and purchased a system like this, once the warranty is expired and that loop asset is not functioning properly, they're forced to either dig it up and repair it, or in most cases, replace that entire asset. So we will cover that cost, and we take that technology risk away from the end user. So as you look at your future developments or your different buildings, if there's any municipal stakeholders on the call today, as you're doing your community energy planning, we've recognized as the utility here and an energy provider of choice that geothermal systems are the future. We believe they're checking all the boxes. They provide increased efficiency compared to current natural gas equipment or propane or fuel oil. They do fit well in the net zero strategy, where you're producing more energy than you're actually consuming just on the geosystem alone. So they fit well. They have a lower energy requirement. Adding solar in to meet that net zero requirement is very easy on these systems. It is a renewable technology. They do provide significant emission reductions, even when factoring in the grid emission, the marginal grid emission factors. By adding these additional electric appliances, geothermal provides what's called beneficial electrification. It will reduce the load during peak periods, and it will actually increase the load during lower consumption periods, which helps balance out that grid infrastructure and reduce the investment required on that electrical grid. And as we discussed, these systems are scalable from a single family home all the way up to an entire community being provided with geothermal heating and cooling systems. We can do it all, and we're looking to be your partner moving forward. So that is essentially all I have for today. We may have whipped through it a little quicker than the hour we were expecting, but I'm anticipating there'll be a number of questions, so we can get to those now if you'd like, Susan.
Sure, we definitely have questions in the Q&A and also some that have been put in the chat. So why don't we start with some of that are in the Q&A. Since you need to install a heat pump and ducts, would the additional drilling to the ground and piping justify a good economic investment? And does it make a difference in the US, a warmer climate?
Yeah, so that's a two-part question. So to the first part, yes, great question, because it is a significant investment. If it depends really on what you're using as your base system. If you're looking at air source heat pump technology, with us providing the loop asset and avoiding that capital cost, we're expecting that because of the performance degradation on a standard heat pump system during really cold winter periods, the requirement to back up these systems with electricity will probably, we're thinking, will balance out with the energy charge that we're charging for the monthly loop asset fee. Air source heat pumps tend to rely on that electric backup during a lot of the winter. So with Geo not requiring that, and of course electric backup is 100% efficient. It's a COP of 1. So your cost of electricity is going to go up, and your energy costs are going to go up the more often that heat pump relies on that backup system. So with Geo not requiring that backup as often, we think it's a great solution as far as energy costs go. The capital costs, I would think the heat pump equipment inside is probably pretty close, depending on which equipment you select, is equivalent to a top of the line natural gas furnace and top of the line air source heat pump if you're doing a combi heating system with or dual fuel system. So I don't think the capital is too far off from an air source option. If you're going base case natural gas, certainly it would be. Cheap gas furnaces are very cheap these days, but I hope that answers your question. And the second part, in the US, these systems are super efficient on cooling. So they're very effective in milder climates. The middle section of the US is very common for geothermal applications. What we have to worry about in the US is a little bit different than what we're looking at in Canada, where we're typically a heating dominant climate here in Canada. So there's a potential to not freeze out the loop, but thermally depress that ground system and its ability to basically disperse that heat into the loop. In the southern US, the same issue happens, but on the opposite side of the scale, where the cooling loads are drastic and they potentially could overheat that loop or the ground surrounding that loop and lose its ability or its efficiency over time. So again, proper engineering, proper design, and adequate sizing of these loops should provide an option for throughout North America. To be honest, these systems have been implemented as far south as Texas and as far north as well into northern Ontario and into the colder climates in Manitoba as well.
Thanks, Jeff. Okay, we have another question. Do you have any recent or ongoing performance monitoring studies in your service territories of the actual annual COP for ground source heat pump systems in new homes?
We do. So the San Diego pilot was monitored for 3 years. We're still monitoring it. We do have extensive data, and our technology and development group, one of the keen engineers there, has actually written two white papers actually that are scientific documents that are currently published, and they show the energy consumption, the COP, and compare it to, I think they compare it to air source equipment, but we have basically monitored them for 3 years now. The seasonal COP, now we have a couple of different heat pumps in that pilot, two-stage equipment as well as variable speed, and the seasonal COP averages between 3.4 and 3.9, I believe, throughout the season, and that's heating and cooling for the entire year. So we do have that data. We can share it. We can share those white papers with whoever's asking the question. They can reach out to me through my email or through Building Knowledge here.
That's great. Should any factors be considered when selecting optimal area for the ground loop?
Yes, depends on the application really, and the ground conditions and the soil types are critical. They really drive the size of that loop. So we typically will do a thermal conductivity test when we're doing larger projects. But as far as positioning those loops throughout the community, if you're looking at a community-based system, like we said, there's many configurations of these. You can go vertical, you can do horizontal in park spaces or field spaces. You can also potentially use stormwater retention ponds and put a stainless steel plate heat exchanger in there to do some of that heat exchange between the water, which basically connects with the ground, and the heat pump system. So there are a number of factors that go into selecting where that loop goes and how big it is and how it's configured. And we would help anybody interested in participating in our program. We would help with that design aspect and the planning process around that.
Next question is, not including the piping in the ground, are the ground source heat pumps actually cheaper to purchase than air source heat pumps?
So it depends on the air source technology you're looking at. A ground source heat pump system is very close in capital cost, the heat pump itself, to a cold climate air source heat pump. So if you're looking at the Mitsubishi cold climate product, the Zubas, or you're looking at some of the other cold climate technologies, the ground source heat pump systems are very close in cost compared to that. One of the challenges we've had in this industry, in the geo industry, is these systems have not been mass adopted. So they're few and far between compared to air source heat pumps, which are very common in the central section of the US. So the manufacturers aren't producing as many numbers of these units. So the cost is a little bit higher because they're not getting as many out the door. We're really hoping that by introducing this program and getting some traction, those manufacturers are going to be able to see some economies of scale and reduce that cost. But if you're comparing to cold climate, it's very similar in cost to a ground source heat pump system.
Okay. The next question, actually, we spoke to a little bit. First part of the question is, will Enbridge be offering long-term contracts to deal with the upfront capital costs? And I think, Jeff, you spent some time explaining the way the new program will work. But the second part of the question is, what sort of obligations does the customer have to Enbridge with regards to annual minimum usage? And what happens if a customer overconsumes?
Yes, so these systems are sensitive to thermal balance, basically heating load versus cooling load over the course of the year. But because we're not monitoring in our single family, single loop application, we're not monitoring energy consumption. We're not charging a metered energy rate. It's a flat rate. So there is no consumption. If the customer chooses to keep their house at 25 degrees Fahrenheit in the winter and 25 C all year, that's fine. If another customer that's energy conscious decides to set it back a little bit and keep their heating a little cooler in the winter and they're cooling a little warm in the summer, doesn't affect their monthly fees. It's a flat rate fee. We're basically just extending that capital out over a longer period of time. When you get into the energy service type agreement on a commercial building, there would be some performance guarantees and some volumetric concerns that we would have there, but we'd be flexible in negotiating a proper contract that fits for both counterparties.
Okay. The next is sort of a 2-point question, but hang on here. So it says, I know that going to a central ground loop heat exchanger may be the way for a lot of the multi-unit housing applications. Question is that applicable for single homes, or a ground for sink for each home would be better? Since most homes are more and more energy efficient, it would take very little to provide a ground loop for these homes. The only concern is the cost of pumping the central ground loop. Now, is that assumption correct, or?
That's a great question, and certainly a heated debate currently. There are a lot of companies or a lot of engineers designing these microgrid or ambient loop type systems. My personal opinion is you'd have to assess the density of that community and also the load profile of that. If you have a community of, let's say, 350 single family homes, they are likely to be heating all at the same time and cooling all at the same time. There may be some periods during the shoulder months where there is some potential for energy sharing, but in a flat community that has all the same type of load profile, that's an absolutely correct assumption. The additional pumping costs and the infrastructure costs to put in that ambient loop in that community may outweigh the benefits of that energy sharing potential. So a single loop per single home application would be more cost effective in that case. But when you get into the mixed communities where you have commercial and retail, especially mixed in with those single family homes, Definitely the ambient systems may come out a little bit to the advantage, but again, it depends on the infrastructure costs and the complexity of that below ground infrastructure. Once you start pumping fluid through, 50 or 100 acres worth of property, there are some significant costs to that pumping, and the infrastructure required is quite costly. So we would assess that and basically provide options to see which the best, most cost-effective solution is.
Thanks for the question, Rose. Next question is, what is the PSI rating of the pipe in the ground? 600 feet deep with the weight of water, can the pipe withstand this pressure?
Yes, great question. So that's a question that comes often, especially to our drillers. The PSI rating, I'd have to check off the top of my head, but it is well in, I think it's about a 3 to 4x factor of what the actual system operates at. So typical systems, geothermal and ambient at the heat pump would see pressures no higher than typically 75 PSI. Certainly, the head pressure on that loop at the bottom of the 600-foot hole would be significantly higher than that. We don't foresee any issues with the PSI rating of the pipe. It's very resilient, but there are some restrictions to the depths, and that's why there's actually a regulation that's being modified right now to maximize those depths. We've had drillers attempt 800-foot shots. There's a couple in Europe that have done over 1,000 feet, and certainly that head pressure of the vertical well and the water pressing down would increase that pressure on the pipe. We would do the proper engineering calculations to ensure that pipe's resilient. It's our asset, so we certainly don't want to burst it, 5-6 years down the road. But the pipes are very resilient.
And I think we have such a long-standing history of putting safety first in just about everything we do. That's one of the attributes that we can offer, because we have so much experience in making sure things are done well, things are done right, and things are done safely. So next question. If the site characteristics that they're working with make geothermal non-feasible, how do gas absorption heat pumps compare to traditional heating systems, furnace and a boiler, to air source heat pumps and geothermal?
Great question. And yes, natural gas absorption heat pumps are a technology we're also looking at. Unfortunately, there are not a lot of products commercialized currently in the residential space. So for residential communities, it is a challenge today. There are a number of manufacturers working on that technology. We're hoping to see more products available in the market within the coming 1 to 2, even 3 years. Certainly, the absorption technology is effective. We're seeing from some of our lab studies and the pilots that we're doing on that natural gas heat pump equipment that we're seeing COPs of 1.2 to 1.7-ish. So significantly higher than a conventional natural gas fossil fuel burning piece of equipment like a furnace or a boiler, but not nearly as high as an air source heat pump technology or a ground source heat pump technology. That being said, natural gas is a very cost-effective fuel. So if you have a COP of 1.7 and you're using a fuel that's 1/4 of the cost of electricity, that technology may start to play into one of the solutions. And certainly, if the geology of the community or the location for that development doesn't lend well to geo, incorporating natural gas heat pumps would be a solution that we would recommend, certainly for increased efficiency.
Okay, so here's a question that we get asked quite often: what happens to this system after their lifespan, and how do you refurbish them once there is a building on top of the borehole?
Yes, that's a great question, and I've been asked that several times. So to be honest, these systems are designed to last. The piping system is designed to last well in excess of 50 years. We're thinking closer to 100 plus years. So ideally, it's going to outlast the life of that building. We're suspecting. In the event that loop does fail or needs to be replaced, if it's installed within the perimeter of the foundation, we would likely have to drill a new borehole outside of the perimeter and penetrate through the foundation like a conventional geo system would be installed. So it's not too critical. We're going to be drilling that loop anyways. We would put one in the driveway or in the front or backyard, and then tie it back into the existing heat pump system.
Is a backup system required for heating and cooling, or can geothermal actually provide the full range of temperatures required by the homeowner?
Absolutely, it can. Depending on the application, if it's a single family home, we can do 100% of the heating and cooling load of the building. Sizing of these systems is critical though. So believe it or not, it's very effective to undersize it slightly. We don't want to do 100% of the heating load. It's more cost effective. And we found in our pilot with San Diego, in a home that requires 3-ton peak capacity, a 3-ton heat pump will produce 100% of that heating load if designed and installed properly. Typically, we would put in a slightly lower sized heat pump and rely on that backup electric heating. It's more cost effective if you're talking 2% of the year to size to 100% of the coldest day of the winter, which happens on a handful of days. It's not as cost effective. So sizing is critical, but they are capable of doing 100% of the heating and cooling. When you get into commercial or multi-unit residential buildings, it's a different story a little bit, and it's definitely a cost issue. So they're often supplemented with natural gas backup systems and or chillers in the case of a cooling dominant system. We want to really balance out that load field over the course of the year. So we may add supplemental heating or cooling depending on the system. But again, we would do the engineering design and run a couple of scenarios to ensure that we're optimized and getting the best bang for the buck.
Question from Aaron, the geothermal fee, is it similar to a regular Enbridge gas service fee or an Enercare fee? Would the bill be like receiving a normal gas bill?
Yeah, so depending on the application and the community, if there's gas in the community for other uses and the homeowners or building owners have a natural gas account, we would be able to bill on that through our open bill functionality. Even though it's offered through an unregulated affiliate, we would be able to access that open billing functionality. And you would basically get your Enbridge gas bill, and then you'd see a line item on there very similar to your Enercare or your Reliance charge for the rental water heater. It would just say geothermal service charge. In communities that don't use natural gas, the billing functionality would be slightly different. We'd probably use one of our other affiliates, either Gazifare or a third-party billing outfit, and you would receive a separate Enbridge type bill for your geothermal services.
A question on large scale. So this question comes from someone who works at an educational facility. So we're looking at approximately 2 million square feet, 15 buildings, with a central heat plant and a thermal loop, presently heated primarily by natural gas reciprocating engines with both jacket and exhaust heat recovery. Are there designs for larger central plant installations that can handle a capacity over 10 million BTUs per hour?
There are. It really depends on the distribution system. If you're looking at high temperature, if you're getting into the high temperature distribution, Geo isn't a perfect fit for that. It's not great at doing 180 degrees Celsius water for sure, but certainly if you have low temperature distribution with fan coils or floor heating, we certainly can do it with Geo. There are heat pumps available to meet those capacities. Certainly that would be probably a balance or a hybridized system where you would still rely on that natural gas. But again, you could also incorporate Geo Exchange just for thermal energy storage that can be collected at a later date, and the heat pumps can supplement those natural gas systems. It really depends on the application.
Okay. Can the Enbridge lease system, hang on a sec, the question just bumped up. Can it work out cheaper for occupants than having a regular natural gas furnace?
Today, it is slightly higher than what the energy cost of ownership would be for a natural gas system because of the cost of natural gas. But as the federal government implements the carbon tax increases over the next 4 to 5 years, we're basically it's going to be at par and will just inevitably get cheaper than natural gas as that carbon tax is implied. Once we get up to $170 a ton with the efficiency of the heat pump and the electricity cost, but again, it depends where electricity goes. Yes, we foresee that in the near future, geothermal will be a lower cost of ownership, even including our monthly operating fee for that loop asset compared to natural gas. As of today, it's certainly much more cost effective than alternative sources such as air source or fuel oil or propane in communities that don't have access to gas.
Okay. Does Enbridge undertake geothermal installations for high-rise developments?
Yes, our commercial program would incorporate high-rise, both multi-unit residential buildings as well as commercial high-rise. This technology does fit in all applications, and we are actively working in that market currently.
And is it you, Jeff, that they would contact if they had interest?
Yes, any geothermal specific projects can come directly to me.
Okay. Can the ground loop go directly under the building, or does the loop need direct exposure to radiated ground?
No, it does. It's very common to put it directly under the building in high-rise applications, especially in redevelopment situations in the city of Toronto. That is the most common application. The ground is one large thermal battery, and heat, depending on the thermal conductivity and diffusivity of that soil, heat moves from hot to cold. So even though the loop field is directly below the building and doesn't have access to that solar radiation, the surrounding ground will reject its warmer energy towards that bore field as it starts to cool. So it doesn't have to have direct exposure to the sun.
Okay. Do seismic considerations need to be taken into account, and can it change the installation?
Good question. We don't have too many earthquakes here in Ontario. Certainly in California, I think we'd probably want to consider some of those seismic. That's a question I've never been asked, to be honest. We don't have too many earthquakes here in Ontario. I'm sure there are engineering requirements for seismic activity. It is a polyethylene piping system that is in the ground and sealed with a bentonite slurry, so I wouldn't imagine there'd be too many issues, but I am not a seismic geologist, certainly, so I'd have to take that one away.
Okay, maybe we can put that in a parking lot and take a look at it, and we can always post something later on for all of our participants. So next question, after 50 or 100 years or whatever the lifespan may be, is the only solution to drill all over again, or are there other alternatives being looked at to replace the geothermal system at that point?
Yeah, who knows? I mean, 50 years is a long period of time. The HVAC technology over the last 15 years has developed quite drastically. So we don't know what's going to be available in 50 years. And it depends on what happens to that loop. It's quite possible the loop can continue to provide reliable service beyond 50 years. But again, yeah, it depends on what technology is available. There might be a better technology to couple to the ground down the road. We may have solar thermal that's a little more effective and able to produce that energy we need. It's hard to say really what's going to happen in 50 years.
Mm-hmm. Absolutely. Next comes from a situation that's happening in the city of Ottawa, where they're struggling convincing the municipality to allow the use of storm ponds beyond what they are for, and the same for parks. Have we had any success with the municipality sharing the use of land, like a park underground for geothermal or above for park use? Any sort of connections from a municipal level?
Yeah, so I think that's a great question. I think that'll be one of the challenges that we face moving forward is whose land are we collecting that energy from, and what other uses is it needed for? Certainly geothermal is out of sight, out of mind, so it can be used in park spaces, soccer fields, recreational fields, etc. Stormwater retention ponds. I actually saw an article the other day. The Toronto Regional Conservation Authority was doing some testing on using GeoExchange to actually manage stormwater retention ponds and the temperature and the related increase in temperature that's causing vegetation issues. But certainly we haven't had any direct issues, but unlike our regulated business, our utility business, where we have an exclusive franchise agreement and an access to that right away, as we get into these community-based systems, those policies will need to be developed and agreed upon moving forward. to be able to put this piping asset in a public space or a municipally owned space or on various properties to harness that community type energy.
Do you have any examples of any Part 3, specifically multifamily, using geothermal systems today?
I can provide a number of them. Yes, they're very common, especially in the city of Toronto, with the Toronto Green Standard really driving that market. Yeah, I can provide some case studies likely as well. If they want to reach out, that questionee wants to reach out directly to me, I can probably steer them in the right direction for some case studies.
Great, thank you. Okay, next question is approximately how warm could you get DHW with geothermal without electric backup?
There are heat pumps currently, water-to-water heat pumps on the market that will produce delivered water temperature of 130 degrees plus, 140 even, I believe, on a commercial type application. But certainly there's a number of manufacturers that make residential heat pump systems that are dedicated for domestic hot water and produce the required delivery temperatures that we see under the current plumbing code.
Okay, there is some requests as well for your email contact. So when you when this ends and we send the information out, we will definitely be sending Jeff's contact information as well for everybody that's participating today. Next question is, what is the recommended frequency and approximate cost for routine service of the ground source heat pump for a single detached home?
That's a great question. And one of the advantages to geothermal systems is they require a lot less maintenance than conventional fossil fuel burning equipment. I personally still recommend annual service, but no more than annual service on that heat pump equipment, and it's much less involved. We don't have to pull burners out or combustion blowers to ensure they're adequately cleaned. We're doing a checkup, performance inspection, and basically just an operational check and a quick cleaning of the refrigeration coils. But basically, once a year is more than adequate.
Okay. Next is, what are the geothermal mechanical room space requirements in a typical mixed use development, sort of in an underground parking area?
Yeah, so it depends on the application. There's a number of ways to do those type of buildings. If you're talking a centralized heat pump system that's delivering energy into the central building loop and the individual suites would have fan coils, then you would need no larger mechanical room than your conventional boiler system. If you're doing distributed heat pumps as opposed to fan coils, and you have a heat pump in every suite, then the infrastructure and the footprint is much smaller because you don't have a central heating plant. You would simply connect that geo exchange loop through a plate heat exchanger into the building loop. So you just need the space for a header basically and a plate heat exchanger in the mechanical section.
Okay, next question is, in the past, this individual has found that the geo equipment energy usage can be high because of the constant pump operations, etc. Is this still the case?
Yeah, so it depends on the application. If he's talking high-rise or multi-residential, incorporating a variable speed or variable flow design into that would definitely help limit the operational cost. It depends really on what they're looking at and where that pumping is. If he's talking the loop field pump, ideally, depending on the loads, it does not need to operate 24/7. But again, it depends. It's very application specific. It depends on how often that circulation system needs to run, basically.
Okay, I'm going to ask this question, Jeff. We may need a little more clarity. He says, can you please talk about water systems, such as ocean or lake, for the energy source?
Okay, yeah, certainly. So there's a number of ways to do water sourced. If he's referring to not open loop, but rather closed loop water source systems, there are a number of products on the market. You can use polyethylene piping, very similar to a ground loop, but it would be installed in either slinky coils laid out on a mesh and sunk to the bottom of the lake or the body of water. You could do tubes. You can also get stainless steel plate heat exchangers that we can install that would basically operate as a heat exchange between the water and the fluid inside the heat exchanger. If that's what he's referring to, there are a number of different options for actually collecting the energy from the water source, like a lake or an ocean. Certain additional considerations need to be met: depth of the water and where the heat exchanger is going to be located, traffic on that body of water, if there's fisheries in there, sensitive habitats, and also when you get into oceans, you have a tidal concern and moving of that heat exchanger. So we want to make sure it's fixed properly, but certainly lots of options, and heat is very easily transferred from water, so it's a great source of energy.
Okay, so next question is, does the Enbridge program apply only to housing development, or can an individual building a home on their own lot access this program? If the latter, can it be either a rural lot with horizontal loops or a suburban lot with vertical loops?
Yeah, so great question, and I get a lot of interest from our webpage on single-family homes that are being built by homeowners. We have designed our program to help alleviate some of the costs associated with the boreholes and the drilling aspects. So we are attracting, or we're actively targeting community applications for this, where we do an entire subdivision or a phase of a subdivision to sort of gain some economies of scale. As we further develop the programs, we will have a one-off or even a retrofit program available where we could do single homes and deal directly with the home builder, like the homeowner or the person building the home, or the occupant of that building. But certainly our program at the onset right now is designed to get those economies of scale, and we're targeting entire communities, whether it be as central or individual loops.
Great.
But stay tuned. We will have a program available for one-off custom home applications.
Mm-hmm. Yeah, this is just the beginning of our new menu of opportunities that we'll be bringing forward. So next question is, are there soil classification restrictions?
Not restrictions necessarily, assuming you're not talking about contaminated soil. Each soil classification has its own properties, and that's really a critical part in sizing these bore fields. The soil conditions and the ability for that soil type to transfer and reject energy is critical. So we would do a TC test or thermal conductivity test depending on where the application is. There's nothing really that is a no-go or a red flag. There are challenges with each soil type though. So rock is great for thermal conductivity, but it's challenging and costly to drill. Granite, for example, is very hard and very difficult to get through. But the field would have to be smaller because its ability to transfer energy is better. Whereas you get overburdened soils that are also challenging to drill sometimes to keep that hole open, but they don't have a great heat transfer. So you would have to ideally put a longer or larger bore field in to accommodate for that ability for the energy to transfer. But certainly there's nothing off limits necessarily. There are challenges with each soil classification, but we would have to do an assessment at the beginning of the project to find out what the best solution is. Sometimes it's just a matter of going 200 feet instead of going 600 feet, or vice versa, depending on the soil conditions.
Okay. I know that you mentioned the different types of heat pumps for GeoExchange, but can you just elaborate a little bit on which one is the most efficient type?
Good question. The water is very effective at conveying energy. So water-to-water heat pumps typically see slightly higher COPs than a water-to-air distribution system. So if you're doing hydronic, and also you're requiring lower delivery temperatures. So on a hydronic floor heating system, you're looking, some of the buildings can be designed for 80-degree Fahrenheit water, which would be very cost effective and super efficient on the water-to-water heat pump. So it really depends on the application, but water is the better energy transfer in my opinion, and water-to-water heat pumps probably have the better efficiency rating overall. But there's other challenges because you have to cool now using chilled water. So there's pros and cons to each. Yeah.
Okay, last two questions. Can you place this under a dock?
Under a dock, like in a lake?
I'm assuming so, in a water source. Yeah.
I am an avid bass fisherman, and if there was a geothermal heat exchanger below the dock, I would be very upset because you're taking that space from the bass. But yeah, yes, you could. Typically, we like to see a minimum of 8 feet to 10 feet of water above the heat exchanger. Depending on the heat exchanger configuration, it could be upwards of a foot to 2 feet tall, depending on how you stack that pipe or the plate heat exchanger. So you could do it under a dock in some of the northern lakes. In the Kawarthas, you'd be challenged to find enough depth at the dock range to get the heat exchanger in there.
Okay, and last but not least, I am interested in this for a development. What do I need to do to plan for this?
So very similar to our gas process, you want to get a hold of us as early as possible in the planning stage. Reach out to me through my contact, which we'll share at the end of the session. Certainly, that would be the first step, to reach out to me, advise your intentions, and then we can get started on an analysis and a pre-feasibility to see what's required and what can be implemented, and work with your mechanical designers as well as your engineers to assess what the best solution is. But certainly, the sooner the better. Even pre-planning phases, like before you get your site plan into the city. Because some of the local municipalities will have certain requirements for us. If you're putting geothermal in, well water protection and groundwater protection policies are in place. So we want to know those up front, but basically reach out to us and we'll guide you through the process.
And for everyone, we have put Jeff's contact into the chat. You'll be getting it afterwards as well, but it is there now for anybody that is interested in contacting him. So with that, we've wrapped up the Q&A, and I am going to thank you, Jeff, so much, and turn it back over to Stephanie Coleman, who'll give you her final messages.
Thanks, everyone.
Thank you so much, Susan and Jeff, very much. And thank you so much for Enbridge for sponsoring this event. So hopefully you found that helpful. I know I certainly learned quite a bit. So at the end of the session and by tomorrow, I'm going to be sending a resource email out, and that will have a link to the recording. It will have a PDF of the slides. And in addition, when the SurveyMonkey pops up, if for whatever reason you miss it or aren't able to do it right now, I'll include that link in there as well, because we'd love to get your feedback. So just before I close things out, I just wanted to mention that next week, Monday and Tuesday, we have Building Science Spring Camp, and that is also sponsored by Enbridge. And so if you're interested in this, reach out to me and I can connect you with where the tickets can be purchased. And for our next month's webinar series, which this particular webinar series is free, we have, I put the wrong slide in there. It's actually Gord Cook is going to be on, and he is going to be sharing with us on building science topics. So feel free to join us next time. I will include a link to the actual session, not this particular one, but I'll include a link to the actual session where you can register for those free webinars as well. So that's all I have. So thank you again for joining us, and I hope you have a wonderful afternoon. I'm going to end the session, and you'll see a little box pop up with the SurveyMonkey link. Have a great day. See you next time.
Thank
Bye.
you, Stephanie. Bye.
Thank you, Susan. Bye.
Thanks, everyone.